Have you ever really stopped to think about what makes laser light so special? I mean, you've got a regular light bulb, right? It just kind of floods a room with messy, chaotic light. But a laser, that's a whole different beast. It's this perfect, tight, focused beam. So what's the secret recipe? How do you cook up that kind of perfect, orderly light? Well, let's break it down. Right away, the difference is just night and day. Ordinary light from a bulb just goes everywhere. Its waves are a total jumble, completely out of sync, and it's made up of a whole rainbow of different colors. Laser light, though, it's the exact opposite. It's incredibly directional, all heading in one tight beam. It's coherent, meaning all its light waves are marching perfectly in step, like a trained army. And it's monochromatic. It's just one single pure color. So the big question is, how do we get from that total chaos to this incredible perfect order? Well, believe it or not, the entire secret is hiding right there in the name itself. LASER is actually an acronym. It stands for Light Amplification by Stimulated Emission of Radiation. And that's not just a fancy name. It's literally the instruction manual for how the whole thing works. So let's take it piece by piece and unpack what it all means. To really get this, we have to shrink ourselves down and think on the atomic level. The whole process, the entire foundation of a laser, comes down to three basic ways that light, in the form of these little packets of energy called photons, can interact with an atom. You can think of it like an atomic light switch, but with three different settings. Okay, so the first setting is the one we're probably most familiar with. Absorption. It's pretty straightforward. You've got an atom just chilling out in its normal, low-energy ground state. Then a photon comes along with just the right amount of energy, and wham! The atom soaks it up. That little jolt of energy kicks the atom up to a higher, more energetic, excited state. Simple as that. The atom is now all charged up.
Now what goes up must come down, right? An atom can't stay in that excited state forever. Sooner or later, it's going to want to relax and drop back to its comfy ground state. When it does this all by itself, it has to get rid of that extra energy, so it spits out a photon. We call this spontaneous emission. And the key word here is spontaneous. It's totally random. The photon can fly off in any direction at any time. This right here? This is what's happening in a light bulb, creating all that messy, incoherent light. And here we go. This is the big one, the absolute star of the show. Stimulated emission. This is the SE in laser, and it's where the real magic happens. So picture an atom that's already in that excited state, just hanging out. Now, if another photon with the exact same energy comes along, it doesn't get absorbed. No. Instead, it kind of nudges the excited atom, stimulating it to drop down and release its own photon. And here's the incredible part. The new photon is a perfect, identical clone of the one that triggered it. Same frequency, same phase, same direction. A perfect copy. So let's just walk through that photon cloning process again, because it's so important. You start with one photon and one excited atom. The photon comes in, gives the atom a little nudge, and boom, now you have two photons. And they're not just any two photons. They are identical twins, traveling together perfectly in sync. This is the amplification part of laser. One photon becomes two, two become four, four become eight. You get the idea. It's a chain reaction, an avalanche of identical light. But hang on a second. There's a pretty big problem here. In the real world, in any normal chunk of matter, you've got way more atoms just sitting in the ground state than are in the excited state. That means absorption is just way more likely to happen than our special stimulated emission. So if we want to amplify light, we have to somehow flip that natural state completely on its head. How in the world do we do that?
Yeah, this chart shows the challenge perfectly. Under normal conditions, what we call thermal equilibrium, the vast majority of atoms are lazy. They're in the low-energy ground state. For a laser to even have a chance of working, we need to create this totally unnatural situation called a population inversion. We have to force the system so that there are more atoms in the high-energy excited state than in the low-energy state.
And just to really drive home how weird this condition is from a physics point of view, it's sometimes called a negative temperature state. Now that doesn't mean it's colder than absolute zero or anything crazy like that. It's really just a physicist's way of saying this is a fundamentally bizarre engineered state that would never ever happen on its own.
So if a population inversion is so unnatural, we obviously have to force it to happen. We can't just, heat the thing up. That just makes all the atoms wiggle around more. We need a very specific, targeted way to cram energy into the system and get a majority of those atoms up into that excited state.
And that process has a perfect name: pumping.
Just like you'd pump water uphill working against gravity, we are pumping these atoms uphill to higher energy levels. And there are a couple of ways to do it. You can use optical pumping, which is basically blasting the material with a really powerful light, like a flash lamp. Or you can use electrical pumping, which is common in gas lasers, where you run an electric current through it to get the atoms all jazzed up.
Okay, but even with all that pumping, there's one more secret ingredient, and without it, none of this works. See, most excited states are incredibly short-lived. We're talking nanoseconds. An atom gets excited and poof, it's back down again before you can even blink. You can't build a crowd if everyone leaves the party immediately. The solution is an amazing quirk of quantum mechanics called a metastable state. You can think of it as an atomic waiting room, an excited state where the atom can hang out for much, much longer. This gives us time to pack more and more atoms into that state until, finally, we get our population inversion. Seriously, no metastable states, no lasers. Now, as engineers got clever, they figured out how to make this whole process way more efficient. A simple 3-level laser has to work really hard because the atoms drop right back to the crowded ground state, but a 4-level laser is smarter. It has the atoms drop to a sort of empty intermediate level first. Since that level is empty, it's much easier to maintain the population inversion. This is the key that unlocked powerful, continuous laser beams.
All right, we've got all our physics principles on the table. We understand stimulated emission, we know we need a population inversion, and we know we need to pump the atoms into metastable states. So let's take all those ingredients from our recipe and actually build a machine. Let's assemble a laser.
So it turns out any laser you can imagine, from a tiny pointer to a giant industrial cutter, is built from 3 core components. First, you have the active medium. This is the heart of the laser, the stuff, whether it's a solid, liquid, or gas, that has those special atoms with metastable states. Second, you need the pumping source. That's the engine that pours in the energy. And third, you need an optical resonator. This is usually 2 mirrors, one at each end, that trap the photons and bounce them back and forth through the medium over and over again, building up that chain reaction until the beam is strong enough to escape.
Now, to see how all these pieces fit together in the real world, let's look at an absolute classic, the helium neon laser. This is the one that makes that iconic bright red beam that you've probably seen a million times. It's just a perfect example of all these principles in action.
So here's the elegant little dance that happens inside. First, an electric current, the pump, zaps the helium atoms and gets them excited. But the helium isn't what creates the light. Instead, these excited helium atoms act as messengers. They bump into the neon atoms and pass their energy over in a perfect little handoff. This creates the population inversion in the neon atoms, and it's the neon that then does the stimulated emission, releasing that beautiful signature red light. It's like a tiny, super efficient atomic relay race.
So why do we care about all this crazy atomic physics? Because figuring this out has completely, utterly transformed our world. And that's not an exaggeration. Modern life literally runs on laser light. From the fiber optic cables carrying the internet to you right now, to the incredibly precise manufacturing that goes into every single electronic device you own, the laser isn't just a tool, it's a pillar of our modern civilization.
But the story isn't over. As this quote from our source material points out, there's a big challenge ahead. It turns out that as you try to make lasers with higher and higher frequency light, like moving up the spectrum towards X-rays, it gets exponentially harder for our hero, stimulated emission, to win the fight against that random, messy, spontaneous emission. This is one of the next great frontiers for scientists to conquer.
And that really leaves us with a fascinating thought to end on. We've seen how mastering visible light with lasers changed literally everything. So if we can crack that next big challenge and figure out how to build powerful, affordable, everyday X-ray lasers, what could that unlock? What new worlds of science, medicine, and technology would suddenly be within our grasp? What could we see and create that's completely impossible for us today?